Hello. In this video, we will do some work on a very simple quadratic equations. Okay, x squared minus x minus 1 equals to 0. This equation can be easily resolved by quadratic formula. X equals to minus b plus minus b squared minus 4ac over 2a. Okay, this is of course 1 plus minus root 5 over 2. Now, we denote the positive root be alpha, and then the negative one will be beta. Now, here's come a very interesting problem, okay? How do we calculate the power of these roots? That is, how do we calculate alpha squared? Of course, we can simply just square it, okay? Instead, we will have a very interesting and simple method to do so, okay? For example, alpha squared will be equals to 1 plus alpha. Okay, because we just directly plug in the alpha into the root equations, since alpha is the root, so that we can replace these two terms to here, we will got 1 plus alpha. Okay, now how about the cube? The cube is easy, okay, because we can split in two parts, alpha square and alpha, and then we put back the answer. What we have will be alpha plus alpha square, and then all the alpha square can be replaced by 1 plus alpha. So we got 1 plus 2 alpha. So the alpha cube will be 1 plus 2 alpha. Now, imagine if you want to calculate this third form to the power of 4, okay? It would be very ugly and nasty, okay? However, using this method, we turn the power into simple additions and multiples, okay, which is easy. For example, how about alpha to the power of 4? Okay, what we have will be alpha cubed times alpha, and then 1 plus 2 alpha. And then again, the calculations is easy. You can do it by yourself. What we have here will be alpha 4 will be equal to 2 plus 3 alpha. Now, we want to do more. Okay, how about alpha to the power of 5? Okay, the calculation is extremely straightforward, okay, but in a very short period of time, you will know we've got a very nice pattern here. Okay, so what we have here is 3 plus 5 alpha. Okay, now what we have here, we can make a list. Okay, alpha square is equals to 1 plus alpha. Alpha cube is equals to 1 plus 2 alpha. Alpha to the power of 4 will be 2 plus 3 alpha. And then alpha to the power of 5 will be 3 plus 5 alpha. Okay, and then of course, for completeness, alpha to the power of 1 of course is 0 plus alpha. Seems that all the columns here are integers, same as here, and then we hope to guess that alpha n will be some integers times another integers times alpha. Okay, it looks so, right? And here we observe that the Fibonacci sequence or Fibonacci's number appears in these equations. Okay, for example, what is Fibonacci's number? Okay, F0 is 1, F1 F0 is 0. Okay, F1 is 1, and the new numbers can be constructed by the previous number. Okay, that is f2 will be 1, f3 will be 2. Okay, so if I just list out all the Fibonacci first few Fibonacci numbers, that will be 0, 1, 1, 2, 3, 5, 8. Okay, so on. Now we see that 0 is here, 1 is here, 1 is here, 2 is here, 3 is here. It seems that these are Fibonacci's number. Okay, you see here 1, 1, 2, 3, 5. Okay, 1, 1, 2, 3, 5. So it would be very nice, okay, if A and B are Fibonacci numbers. Okay, so if this is n, okay, if this is n, which Fibonacci numbers here will be? Okay, we note that this is 0, 1, 2, 3, 4, 5. This is f5. Okay, and then we see here this is f5 and this is f4. Okay, so we guess this is n minus 1, this is n. So we guess our higher power of alpha will be in this form. That is the n minus 1 Fibonacci numbers plus the n Fibonacci numbers and times alpha. Okay, for n is greater than 1. Okay, of course, this can be proved. This is true. Okay, can be proved by induction. Okay, very easily. And I will leave that as an exercise for you. Okay, now the idea is that since alpha is the root of the of our equations, okay, x squared minus x minus 1 equals to 0, alpha and beta are the roots. Okay, so the whole idea, okay, will also be valid for beta. Okay, so we will have beta to the power of n is equals to fn minus 1 plus fn beta. These expressions will also be true, okay, because beta is also the root of these equations. Since the discussions for the alpha is just the same for the beta, okay, we can simply just transform alpha into beta, okay, to give these expressions. Okay, now this is the equation 1, this is equation 2. If we subtract 1, if we subtract 2 from 1, okay, we got alpha to n, beta n equals to fn. Okay, so we got an explicit expressions for the Fibonacci number. Okay, that is fn is equals to alpha to the power of n minus beta n over alpha minus beta. Okay, of course, alpha and beta are already calculated previously. Okay, we know these two answers. Okay, so we can put it back. That would be 1 plus root 5 over 2 to the power of n minus 1 minus root 5 over 2 to the power of n, okay, and all together over root 5. Okay, because alpha minus beta is root 5. Okay. Okay, so we prove that the Fibonacci numbers can be expressed in terms of these expressions. Okay, full of root 5. Okay, amazingly, although there are many root 5 here, all these are integer. Okay. Okay, all these are integers. Okay. Now, it would be very interesting to note that if we use alpha and beta to express the Fibonacci numbers in this form, okay, what will be alpha n plus beta n over alpha plus beta, okay? What is this? Okay, why we want to ask these questions? Because you see these two forms are of very similar. Okay, very similar. We want to know if this guy represents Fibonacci's number. These are all minus signs here. What if we change the minus sign into the plus sign? Okay, what will be this guy? Okay, we will investigate this. Okay, now from the very beginning, our equations x squared minus x minus 1 is equal to 0, and then we also know that alpha plus beta will be minus b over a, right? Minus b over a. Okay, that will be 1. So we know that alpha plus beta is 1. So let me call this guy Ln, okay? Be alpha n plus beta n over alpha plus beta, okay? We don't know this guy. And then we know that alpha plus beta is actually 1. So this expression is simplified, okay, to alpha n to the power alpha n plus beta n, okay? Now, we have no idea what is this, okay? So we plug in some numbers into it. What's L0? L0 will be alpha to the power of 0 plus beta to the power of 0, which is 1 plus 1, which is 2. What is L1? L1, of course, is alpha 1, beta 1, which is 1. Okay? How about alpha 2? Alpha 2 will be alpha squared plus beta squared equals to, okay, we don't know, okay? But we know that this is sum of root. This is the product of root. Product of root will be 0 over a, which is minus 1. And then we can do some tricks on it. Okay? We know alpha plus beta square, which is alpha square plus 2 alpha beta plus beta square. So we minus 2 alpha beta here. And then we'll plug in numbers we know. Okay? That would be 3. So now, n 0, 1, 2, 3, 4. This is the Ln, we don't know. Okay, this is 2. This is 1. This is 3. Okay, 2, 1, 3. Okay, what is L3? Okay, basically you just do the direct calculations here. And then we know this can be factorized into this form. And then we put in all the information we have. This is 1. And then the alpha square, beta square, we know already, okay? This is L2. So we have 3 here, and a minus alpha beta, which is minus 1. So we have 4 here. So L3 will be 4. It seems that the next one will be 7. Okay? Why? Why is that? Just like Fibonacci sequence, this is 0, this is 1. Okay, and then the next one is the sum of the previous 2. Okay, so we have 1 here, and then 2 here, and then we will have 3 here. And then we guess, okay, we guess L4 will be 7 because we just sum the previous 2 guys here. Okay, okay, let's check. Okay, let's check. L4 will be alpha to the power of 4 plus beta to the power of 4. Okay, how do we proceed? Okay, we consider alpha square plus beta square is equal to alpha 4 plus 2 alpha square beta square plus beta 4. Okay, this is what we want. Okay, so alpha 4 plus beta 4 will be equals to alpha square plus beta square, and then all square, and then minus 2 alpha beta all square. So we just plug in the number we have. This is 3 squared minus 2, and then alpha beta. Alpha beta will be minus 1, but it is squared, so we have 7. So indeed, this is correct. Okay. So it seems that our Ln satisfy the following conditions, which is L2 is 0, and then L1 is 1, and then the new guy is the previous two guy sum. Of course, you may notice that this is very, very, very similar to the Fibonacci numbers. Okay. In fact, this is called Lucas number, which is a brother of Fibonacci numbers. Okay, they have very, very similar definitions. The only difference in the definition is that the initial conditions are different. Okay, we see here, just the same. Okay, sorry for that. Okay, just the same, except the initial condition, one is 0, 1, and is 2, 1, and the recurring conditions is the same. Okay, sorry, I made a mistake here. It should be 0. Okay, now you can prove this, of course. Okay, you can prove this easily. Okay, they satisfy this recursive relationship. Okay, how to do so? We have Ln is equals to alpha n plus beta n. Okay, of course we have alpha plus beta here. Of course we know alpha plus beta is equals to 1. Now we want to check Ln plus 2, it is rather equals to the Ln plus 1 plus Ln. Okay. Now we just perform the direct calculations. Okay, we just perform the direct calculations. So we want to prove whether this is true or not. Okay, now on the right hand side, we can factorize alpha to the power of n. Okay, and then we know x squared minus x minus 1 is equal to 0. Okay, since alpha and beta are the roots, so alpha plus 1 is just equals to alpha squared. We know that, right? And then beta plus 1 is equals to beta squared. So we plug in, that would be alpha squared, that would be beta squared. So we combine these two terms, so we got alpha n plus 2 and beta n plus 2. Indeed, this is what we want. Okay, therefore this recursive relationship is correct. Okay, so to summarize, what we have is this: Fn is equals to alpha n plus beta n over alpha plus beta, and Ln is equals to, okay, I make a mistake again, sorry. This is alpha is minus, okay, and then this is the plus sign here. Okay, and then what is alpha and beta? Okay, basically just to remember, alpha and beta are just the roots of these very interesting quadratic equations. Okay, and of course these equations got a name, it's got a Binet formula. In the next video, okay, we will do some work on these two guys, okay, and have fun. Thank you for watching. Okay.